Outline the refining principles of metals by the following methods. Number 1, zone refining. We have explained zone refining in a previous question. NCERT loves repeating questions, although they're asking very simple and small questions, they are repeating also. So I'm not going to repeat the answer, but for those who are keen to just see this, take a look. I've explained this very beautifully before, so I'm just giving you a screenshot. Take it, and if you want the explanation, I've explained before. Then we have electrolytic refining. How is electrolytic refining done? Well, it is done very beautifully. First of all, you have to choose electrolyte, anode and cathode, and this is how electrorefining is done. I'll give you an example, electrorefining of copper, for example. In that case, you take a huge tank and you take a huge block of copper, and that huge block of copper functions as an anode. Huge block of impure metal, say for example copper. This is anode. Oxidation will happen here, and then you have thin strip of pure metal, and this functions as cathode. Yes, this functions as cathode, my dear. And do we have a solution? Of course we have a solution, and the solution contains, well, guess what does it contain? It contains the electrolyte. For example, in case of copper, this is copper sulfate plus a tiny bit of sulfuric acid, just to maintain the solution slightly acidic. Now, what are the principle? The principle is this. If current is passed, now listen very carefully, if current is passed through this setup, you find at anode oxidation occurs. At anode oxidation occurs. And copper is, because copper is present in huge quantities, it is oxidized to copper ions. We mentioned that it also contains impurities like, say for example, iron and manganese. So small quantities of iron and manganese are present, and as copper gets eaten away, just imagine this is a copper surface, and slowly, you find that this surface gets eaten away. Why? Because as copper undergoes oxidation, you find that slowly, the surface particles leave the solution, and they get oxidized and they pass in the solution. Now just imagine, had there been a particle of, say, iron here. The moment iron is exposed, iron says, wow, I can also undergo oxidation because I am more reactive than copper. And you find that iron also passes in the solution as aqueous ions. Iron and manganese, both, all the metals which are more reactive than copper, or whichever metal you are trying to electrorefine, those more reactive metals will go in the solution very quickly, and happily they'll jump and they'll be dissolved. Oh my God, there are impurities? Yes, just wait. And there are also metals which are below copper or below that metal in reactivity series, like silver, like gold. So what happens? What happens is, as slowly and slowly the boundary gets eaten away. What I mean by gets eaten away means it starts reacting and it starts dissolving. You find that this gets removed, and as silver comes to surface, and if the particles surrounding silver, if the copper particles around silver are gone, there is nothing for silver to get stuck to. So silver just falls down, and as it falls down, it forms what is called as anode mud. Okay. So metals which are less reactive come down, like silver and gold. It's a very rich mud. They come down to anode mud. The metals which are more reactive, they pass in the solution, and since huge amount of copper is there, copper also passes in the solution. So the solution contains all these ions. Now, since copper is present in very large quantity, A, and B, when it comes to reduction at cathode, reduction happens. Which metal has best tendency to undergo reduction? Obviously copper. because metals below copper are not even oxidized. They are removed anyways, and the metals above copper have no tendency to undergo reduction. They'll say, we will sit in the solution, we are not going to undergo reduction. So iron and manganese and all such metals are left in the solution. They are left in the solution. And only copper ions undergo reduction because they have greatest tendency now to undergo reduction, and they get deposited. So all the impurities are either in anode mud or they're left in the solution, and pure copper gets deposited. And this, my dear, is the principle for electrorefining of any metal, not just copper. Copper is an example, but for any metal. For those of you who are looking for notes, you can take screenshots and feel happier. Electrolytic refining of metals. Vapor phase refining is, well, very interesting, but again, it's very selective. Not all metals can be purified easily by vapor phase refining, but the concept is this. First, the crude metal, whatever is the impure sample of metal, is taken. It is reacted with something and converted to a more volatile, a significantly more volatile compound. That sounds vague, then I'll give you two examples. One example is Van Arkel's process for titanium and hafnium and such things. And the second example is Mond's process for nickel. What happens? Say, you take a metal, say you take titanium, you react it with iodine and you get TiI4. This is volatile. Now, the first principle is you take crude metal, you react it with something which converts it to a volatile compound. In a first case, this is an example of Van Arkel's process. In this case, the example goes for titanium and iodine. This is more volatile. This is the kind of box which is there. There is a heated filament and there is titanium here along with iodine. They react. As they react, it is hot, it becomes volatile, it goes up. And as it goes up, this comes in contact with a white hot tungsten filament. And the moment it comes in contact with the filament, which is hot, TiI4, it breaks up. It decomposes back to titanium and iodine, and titanium gets stuck on the filament. Iodine is volatile, so it evaporates off, it again condenses, falls down. Again it reacts with more titanium, again it comes up, again titanium gets deposited here. The process keeps on repeating till all the titanium has been deposited, and at the end you can simply drill a bore, remove the inner core of the extra metal, and you have pure sample of titanium. This is how you can do a vapor phase refining. So the concept is reaction of crude metal with a substance which produces a volatile substance, and this volatile substance on heating should be able to decompose back very easily. This is the principle. Another example is Mond's process, a very favorite process. I can't help giving you this example. Nickel is reacted with carbon monoxide to produce the volatile NiCO4. And if you heat it to a bare minimum temperature of 150 degrees Celsius, it again decomposes back to nickel and carbon monoxide. So first you take crude nickel, react it with CO, it vaporizes forming an NiCO4, take it to a second chamber because it's vapor, it can flow very easily, and now heat it. It decomposes, it gives you nickel which deposits there, and carbon monoxide, you take CO back and keep on recycling. And this is how you can do vapor phase refining for nickel as well. These are the two examples of vapor phase refining of various metals. For those who want a written answer, this is the answer. Well, the principle has been written down clearly.